Hi AP Stats, this is notes for 8.1. We're starting a new chapter called confidence intervals. So confidence intervals are going to be our guess at what we think the population actually looks like based on sampling that we covered in chapter 7. Okay, so we're starting out with a level C confidence interval has two basic parts to it. The first part is calculated from the data, that's our estimate. Okay, that's either our proportion estimate or our mean estimate that we would have probably gotten by sampling. Then the second part is a margin of error, or how much I could possibly be off by in my guess. So I might decide that 50% of my AP students do homework plus or minus 40%. So what am I really saying? Well, I'm really saying that I think it's 50%, but I could be off as much. I could vary from that 50% by as much as 40% in either direction. So I'm essentially saying that I think somewhere between 10% and 90% do their homework. That's a pretty safe bet, right? So the bigger our confidence interval is, the bigger the margin of error is, the more confident we can be because we are spreading out that variability so much to catch the true mean or the true proportion. All right? So confidence level C gives you the probability of the interval, which will capture the true parameter. And the true parameter, again, is either a proportion or a mean. Okay. Value in repeated samples, C is given as a decimal since it's usually a probability value. All right, so here is some of our conditions that we need to check for before we try to construct or create a confidence interval. And we're going to do a population mean first. So we're going to be doing mu first. All right, so the three big things that we are looking for is we want to make sure that our sampling is coming or our data is coming from a simple random sample from the population. Excuse me. So if I can't get where the presentation of the problem says SRS, the other thing I will take is the word randomly selected. So if they say randomly selected, we're going to say that's close enough to an SRS. The other thing we need to check for is normality, and we've already been doing this in our sampling. So either the sample is drawn from a normal population or approximately normal population, then we know that our sampling from that should be approximately normal as well. Or because it's a means problem, we can do the large sample size n is greater than or equal to 30. Remember, that was called the central limit theorem. So these checks that we were doing before don't go away. Central limit, ooh, that was good. Central limit theorem. All right, we're actually going to add one of, let's say they don't have either one of those. They didn't say it was the normal population. I don't have more than 30. Let's say I have 28. Well, if it's a small sample size, we want to look at or graph the histogram of what you do have. And as long as there are no major skews, we're just going to say will continue. We'll acknowledge that we can't assume it's normal because of the central limit theorem, but the graph doesn't look bad enough for us to stop. Okay? And then the third one is the independence one. We've been calling this the 10% rule, and we're trying to make sure that all of our observations in the sample are independent. So this is the one that is 10 little n has to be smaller than big N, where little n is sample size and big N is population size. Okay, if they don't give you population size, just like before, we put in our sample size instead, and we say we believe it's reasonable that the population size is more than whatever the number was for 10 times n. Right? All right, so some of the newer stuff we're going to go and calculate. We're going to calculate something called a z-star score. Now, you already know what a z-score is, and this is very, very similar to a z-score. That's why they're using the same letter. Okay, and the z-star score is related to our confidence level under a normal curve, and it's really lying between a negative z and a positive z. So we're going to think of z-star as the number of standard deviations away from a mean. That's kind of what we thought about z anyway. So let's show you what we mean here. So let's draw a normal curve. And we're not going to mark anything on the x-axis. So nothing along that horizontal line. We're going to try to identify where the middle 90 is. Because remember, my guess, I'm hoping, is going to be right here. So I'm looking for, if this is 90% and it goes from here, and I'm just guessing at where it goes to. Let's say it goes from here to here. So 90% goes for all of this section underneath the normal curve, right? Then the question is, what is this z-score and what is this z-score? So we're going to have to do some inverse normal stuff to figure this out, right? But before I do that, I do want to figure out what's left in that normal curve. So first thing is, I know I have 100%, that's the same as a decimal 1, and I'm going to subtract out that middle 90. That's going to leave me with 10%. Now that 10% has to be split among both tails for each tail. So that means each tail is 0.05 for this section right here and for this section right here. So remember, when we found inverse norm, we would go backwards. So we would say that this is inverse norm of 0.5, and that would give us just that empty space on the left, but it would tell us where that empty space stops. It would tell us where that negative z-score is. So that's going to give us a negative value. Or I could go for the right one, but remember, I have to accumulate everything from the left there. So if I accumulate everything, it's going to be 0.05 plus 90. So it would be 0.95 to get to the positive z-score. We really just want to know what that z-score is, and we really don't want to have to identify if it's plus or minus, which is why we switch to the star symbol. So if I go and I grab my calculator, and I'm doing this off screen, I apologize. If I do inverse norm and I do 0.05, I am getting negative 1.645. And what do you think I'll get if I do inverse norm of 0.95? You're exactly right. Same exact z-score, it's just the positive. So we would say in this problem that z star equals 1.645. We're basically just not worrying about whether we're at the left corner or the right corner. We're just saying that the standard deviation from the mean, either direction, is a distance of 1.645. So the star just means a distance instead of a plus location for z or a negative location for z. Cool. So we're going to do this for a few of our favorite ones. These are the most common ones that we tend to see in confidence intervals. Okay, so again, these are called confidence levels, are the proportion of the normal curve that's in the center surrounded by that middle amount. All right, so let's do this one again. We'll do this one with a 95. So we have a 0.95 in here. It's going to go a little bit further out, and I'm basically trying to figure out what's left. So if I subtract out the 95 from the middle, that's going to leave me 5% that I then need to divide among the two tails. That's going to give me 0.025 for each one of these sections, 0.25. So if I want to figure out where either one is, I'm going to do inverse norm. Now, if I decide to do inverse norm of 0.025, I'm still going to write down just what the positive is. So I'm just going to do the sign change in my head. Or I could do inverse norm of 0.9, sorry, this one goes there, that one goes there. So the 2 will get added to the 5, so we'll get 7.5. Okay. Again, you can do either one or both, right? We just want to get to a z-star score. So if I do this one, I will get that z-star equals, what is it going to be? Again, give me a second, I'll put that into my calculator. So inverse norm of is going to be 1.95996. So I'm going to call that 1.960. So that's my z-star score for a 95. Now, do you remember when we first learned about those standard deviations as percentages, and we said they were 68, 95, 99.7, right? So notice that this is a 95, and we're not exactly at 2. So that's why if you're using those percentages, 68, 95, 99.7 as part of a normal curve number, and you're using those percentages that go with it and the standard deviations, you want to say that's from empirical rules so that they know you didn't get it from your calculator, because your calculator would not have given you exactly that percent or exactly 2 standard deviations. Okay, it's kind of like a rounding error thing. All right, let's try the last one. And the last one is 99% confidence level. So that means we're going to have a 99 in the center of our normal curve. And we're going to do 100% minus 99%. That's going to give me 1%. I'm going to divide that by 2 for each tail. That's going to give me 0.005 for those end little pieces. So if I do this one as inverse norm, and I'll do 0.005, and again, when I calculate it, I'm just going to take off that negative sign that comes when I do it this way. So I'm going to get 0.005. And this time I'm going to get a z-star score of 2.576. Cool. So those are basically our distance in standard deviations from the mean. And that means either way, left or right, positive or negative. So the star is just another way to say distance or only the positive version. All right, so next is confidence interval for population mean, and this is going to be one where we know the standard deviation. Okay, we're still talking about mean. We haven't changed our category any. Now they're just giving us an extra little piece of information that is telling us that our population standard deviation is known. Okay, so here it says choose an SRS of size n from a population having an unknown mean called mu and a known standard deviation called sigma. If the conditions are met, then X bar has the distribution. And we would be saying it has a distribution and a confidence level of mu is. So let's take a look at this. How would we do a confidence interval? So we would start out with our first guess. So we think our guess is whatever we got from our samples. We just average them together and go, this is our guess for the mean, for the missing mean. Then I would do a plus or a minus. And after this is my buffer zone. Remember when we did percentages, right, of how many did homework, what percent did homework? I added on or subtracted from 40. That's our next part. That's going to come from taking the distance of our standard deviations and multiplying it by a standard deviation. So that would be multiplying it by sigma over square root of n. Okay, so this part right here is called our margin of error. Or another way to say that is ME, margin of error. And again, sometimes error sounds a little bit weird, so you can also think about this as margin of variability. All right, so we're going to get a number like 50 plus or minus 40. All right, so we might start out with a number like 50, so example, 50 plus or minus 40. Well, what do I know about that? I know that the low would come from doing 50 minus 40, which would give us 10, and I know that the high amount would come from 50 plus 40, which would give us 90, and so they'll write it as an interval. So they'll go from low to high, and they'll say it's 10, 90, like that. So this would be our low value. This would be our high value. And they got that from writing out first what their guess was and then what their standard deviation is. But it's a standard deviation multiplied by the actual standard deviation for that item multiplied by how many standard deviations that is. So that becomes margin of error. Okay. All right, so C is the confidence level, X bar is the sample mean, Z star is that value, right, the number of standard deviations left or right, okay? So next is we're going to work this backwards. We're going to ask you to interpret a 92% confidence level versus a 92% confidence interval. So I've been using both of those and you might not have noticed the major difference there. So we want to make sure that you see what the biggest differences there are. Okay. All right, so let's do confidence level first. If we have a confidence level first, what we are basically saying is that if we take many samples of the same size, so same little n, from this population, about 92% of them will result in an interval that captures the true parameter value. Okay, so this is for confidence level. Okay, so what does that actually mean? We'll go over this some more in class, but basically the idea here is every time I take a scoop, right, there's a certain number of little n's in that scoop. And once I take that scoop, I'm going to average that scoop, right? And not only am I going to average that scoop, but I'm also going to find its own little confidence interval of like, this is my guess, this was the lowest I saw, this was the highest I saw, kind of like a 5-number summary. And I'm going to say that's my interval. And I'm going to do that many times. And at the end, we're saying that 92% of those times, 92% of those scoops where I took them out and I put down what their mean was, what their spread was, the entire thing captured the true mean. So each one of those little mini X bar samples actually happened to contain the real number we were really looking for. That means 8% of them were either way too low or way too high to even come close to including the actual number that we're investigating. So that's what we're saying about. Okay, so it's the idea that if I take many samples, about 92% of those samples will result in intervals that capture the true parameter value, the true mean or the true proportion. Okay, in the next one, we're talking about a 92% confidence interval. So this is usually us describing that 10,90 part up there. So for that one, we want to start out with, we are 92% confident that the true mean or proportion, so the true mean or proportion falls between, and then we give them the interval, between low interval and high interval. Okay, so in our previous case, we'd be saying we're 92% confident that the true mean or the true percent is between 10% and 90%, and we're 92% confident of it. Okay, all right, so moving on from there, we're going to talk about what steps we're going to have to take in order to find a confidence interval. So we know how to calculate it, but remember, calculations in stats is only a very small part of it. The rest of it is your ability to explain what you're doing. So when we're doing a problem that involves doing confidence intervals, we're going to remember the word or the letters for panic. That's going to help us remind us what every single thing is. So here is the main idea. And again, we'll practice this some more. P stands for parameter. Okay, so we want to make sure that we describe in words and in symbols if you're able to, in words, what we are looking for. So we are trying to estimate or trying to find the true mean whatever of whatever. Okay, and you write that down in words. The next thing we do is we're going to go and we're going to check our assumptions. So those are the ones that we've been repeating. So those are the ones of we want to make sure that it was random. We want to make sure, so an SRS hopefully, we want to make sure that we can assume it's normal, and we want to assume that independence part, right? So that's that 10 little n and big N. Okay, so we're going to go and check all of those and make sure everything's good to go. Then the next part is we're going to name what we're actually doing. This is going to be a consistent step over the next several chapters. So we're going to name the interval. So in our case, the one we are doing right now as an example is we are doing a confidence interval for means. Okay, and it's actually a one sample, meaning we're not comparing two different numbers like a male versus a female. Okay, so that's really hard to read. So it's the name of the interval, the confidence interval for mean, and we'd say it's a one sample, only because we're not comparing like a male to female or different groups. Okay, all right, and then the next part, I. This is where you actually calculate the interval. Okay, don't go straight to the answer, show the setup, show your numbers in the calculation. Okay, and then go ahead and calculate all the way through the calculation. So you're going to start out with whatever that number is, plus or minus the margin of error, right? And then that's going to lead you to your low and your high interval. Right? And then the last step, probably one of the most important steps that people seem to leave off the most, is conclusion. Conclusion in context. So that's our confidence interval statement. We are 92% confident that the true mean is between, right? And that we repeat back whatever it is about the parameter that we are trying to achieve. So by C, we should be saying, okay, here's our final answer, here's how you would interpret it, and here's what it stands for. Okay, so a lot of writing to just do that little bit of math that's right at I, and maybe a tiny bit at A. Almost everything else is a logical reasoning paragraph, basically. Okay, all right, and then some other key things to keep aware of is increasing the confidence level increases the margin of error, right? So if I go from a 50% to a 75%, right, then I'm going to be spreading out that normal curve further left and right. That increases my margin of error, okay? Increasing the sample size leads to decreasing the margin of error. So why is that? As n goes up, we know that variability goes down. Variability decreases, and variability is another way to say margin of error. It's margin of variability, so it's same concept as last chapter. All right, so let's go through and do a couple problems that are easy enough for us to do without having to do the full panic write-up, because we want to kind of do a few of those together in class. All right, so here we're going to work on just finding little n in different problems. It's an easy way to kind of work our way into these. So before conducting a study, it's useful to set a desired margin of error. So for example, if I am dealing with something in the medical world, my margin of error might be very, very small if I'm working with microorganisms, right? Or if I'm trying to do a space calculation, I might want to have a very, very, very small variability to whatever the true number is. But if I'm just working with how many people have trash cans on their front lawn, like that doesn't have to be that specific with that small of a margin of error. I could probably get away with a bigger one. So if we want our margin of error to be at most m, then we're going to solve for n, and we're going to give you some examples to do that together. Okay, so the first one, suppose we want to construct a 95% confidence interval for the mean height of NBA players, where we actually happen to know the standard deviation of 8.6 for the entire population, and the margin of error is at most 5 inches. How large must our sample size be? Okay, so here's what we're going to do first. We're going to go first and go find our z-star score. So we're going to start out with this is we're looking at it being x bar plus or minus z star, right, times standard deviation over square root of n. Okay, so I know that their average that they say it is, we have no idea, right? Because they're actually asking how large for my sample to be, what numbers can I plug in? So I know that the 8.6 is actually the standard deviation of the population. So I know that that's going to be after the z star, it's going to be up here at 8.6. They already told us they want us to find n, so I already know I don't know that. And I'm going to highlight it here. Notice that they said margin of error. So that means I'm only working on this part of the equation. So that means I do not need to worry about this front part at all. They're just asking me to get to a certain margin of error, certain variability. And the variability that they want me to be at, so I still have the z star I have to work out, but I'm going to figure that out from the 95%. And we want to make sure that that calculation is at most 4. So the side that I have all the variables in, I want to make sure that calculation is 4 or smaller. All right, so let's go find that z-score again. We can look back on our notes, or I'll do it again for you really quickly. We have the 95 in the center. That leaves me 5 for the outside edges. That leaves me 2.5 once I split them. So I'm going to do inverse norm of 0.025, and then I'll just take off the negative sign when I find it. Okay, and that's going to give me a z-star score of 1.96. I'm going to plug that into the formula too. So here we go. So working on our formula, we've got 4 has to be bigger than or equal to 1.960 times 8.6 for the standard deviation of the population over square root of n. Okay, now I could just guess and check and try to get to the number closest without going over 4, or I could do some algebra here and try to solve for n. If I'm going to do the algebra, keep in mind that n is in the bottom part of a fraction, so I'm going to actually move that over first. Okay, so now I have 4 times square root of n is greater than or equal to 1.960 times 8.6. So let's get square root of n by itself first. So square root of n plus or minus 1.960 times 8.6, all divided by 4. And then last thing is, if I want to get n by itself, I have to take all of this and square it. Okay, so grabbing my calculator, I'm going to do all of that calculation first. 1.960 times 8.6 divided by 4. Get my answer there and then square it. So I am getting that it is 17.757, or let's say 8. Okay, that's exactly to make it equal. They said that they want to make sure that they are less than that. So it's either going to be a 17 or an 18, right? So remember that as your n increases, your variability goes down, right? So if I increase it, it will get smaller than 4. So if this is exactly 4, I want to increase it to the next natural whole number if this is how many we should be sampling from the NBA. So we're going to make sure that we write, so we have n should be greater than or equal to 17.758, or another way to say that is n should be 18 or more. Okay, and they said our sample size must be at least 18 NBA players. Okay, how large must our sample size be? It should be 18 or more. All right, let's do another one just like that. Okay, so this one is, suppose we want to estimate the average height of a Hart High School student within a ½ inch of their true value with a 99% confidence. Okay, if the standard deviation is known to be 2.3 inches, how big of a sample will we need? Okay, so let's go and start working on this one. So let's see, so again, we're doing x bar plus or minus z star with sigma over square root of n, and again, because it's margin of error, I'm only focusing on this amount, and I get to ignore this, okay? So what is the number that they said they wanted to be within? They wanted to be within 0.5 inches. So 0.5 should be the most we ever get. So the other side is going to be less than. We're going to start plugging in all of our stuff. We've got 2.3, we don't know n, and we have to go find our z-score, or a z-star score. So this is a 0.99. That leaves the outside edges to be 0.005. So I'm going to do inverse norm of 0.995 if I wanted to find, let's say, this one. Okay, and that is going to give me a, what is that one? I forgot already. Let me go do that one again. Inverse norm 2.576. So same deal here, we want to solve for n, so I'm going to move n over and move the 0.5 over to the right. So that's going to give me a square root of n over here. We're going to have still the 2.576, the 2.3, and now the 0.5 goes under here, and then we're going to square these. So n should be more than or equal to 2.576 times 2.3 divided by 0.5 gives me 11.8, and then I square that. I am looking at 140.41 people in our sample. Now I want it to be more than that, right? So if I say 140, I'm too small. I want it to be more than that. So I should be picking sample size should be 141 or more. Cool. Move that up so you can see it. All right, our last one. I'm sorry this is taking so long today. A poll taken by a not to be trusted stats teacher asked a random sample of Hart High School students how old they thought she was. Based on this poll, the 95% confidence interval for the population mean was 26 to 56. Okay, so they are 95% confident that her true age is somewhere in that interval between 26 and 56. So if we wanted to interpret this confidence interval, we would want to say we are 95% confident that the true mean age is between 26 and 56. Okay, what's the point estimate? That means what was the guess? Well, the guess was somewhere between 26 and 56, right? I want to find the middle between 26 and 56. So to find the middle, I just would have to find the midpoint, right? Think about it as a number line. If 26 is over here and 56 is over here, what number is in the middle? Okay, so to do that, we can just use the midpoint formula, 26 plus 56 divided by 2, or you could find the distance, cut it in half, and either go down from 56 or up from 26. So this is going to be 82 divided by 2 is a 41. Does that sound about right? Yeah, a span of 30, 15 more from the bottom. Yeah, that'd be 41. So their guess was that this teacher is 41 years old. Okay, and then what's the margin of error? Well, the margin of error is how far we are from the original guess. So how far are we? We would take our guess and subtract it from one of the edges and then take the absolute value of it because it's a distance. So we could do it that way, or we could do 56 minus 41, right? Or any of those, you're just going to take the positive distance. So the margin of error is going to be plus or minus 15. Yes, plus or minus 15. Yep. Yep. So plus or minus 15 years. Cool. So if they give us the confidence interval, it's pretty easy to see where the middle guess is, and then to also see what the margin of error was. All right, thanks for hanging in there, guys. We'll practice this more next time.